this. Okay, so if you have watched the videos, right, on the hazard identifications, there is one part talking about HAZOP. But today I want to emphasize a little bit more about like what HAZOP analysis is, because this is very important, not just for us to do our assignment, because your assignment ones will, some of you will touch it, some of you may not. But it is also very important for us as a process engineer when we start working in the industry. Most of the oil and gas are using HAZOP, and also even semiconductors and some other industrial, chemical industry, they're using HAZOP analysis. So let me just open up my slides on this one. Okay, the ones that you're looking at is the HAZOP concepts. HAZOPs normally is done in a group. Okay, so meaning we won't just do HAZOP like alone, but in your exam, in your final exam, definitely there will be one questions on HAZOP. It's just to test you on your understanding of like how HAZOP been carried out. Okay, so but if let's say you want to do a comprehensive HAZOP analysis, it's always needed to be done in teams. And then you want the teams of diverse background, meaning you do not want them just from engineering itself. You want some of them from production, even some of them from production planning, some of them from QC departments, the quality control departments, so that you look at different level of like what could go wrong and how do you want to prevent it. Okay. So in HAZOPs, we use something what we call a guides word. Okay, so what you need to start HAZOP is that first you need a PFD diagram or you need a PNID diagram. So process flow diagram and process and instrumentations diagram are very different, yeah? Piping, sorry, the PNID is not process. PNID is piping and instrumentation diagram. Process flow diagram will tell you the process itself, and PNID will tell you how is that being connected? What are the valves and all the additional instrumentations that is being added on, especially on control system, being added on to the PFD. And then you also need to know what are the equipment specifications and the material of your equipment. And of course, your M&E balance, your material and energy balance. And so those are what is needed. Okay, so when we start doing HAZOP, we always look at a process flow diagram and then we go into the PNID. And you want to know what you want to assess because it is a very detailed assessment. So normally we start with the general one like flow, level, temperature. If you are talking about, for example, a reactor or a storage tank or any vessel. Okay, so then we do use guide work. Okay, so I'm going to skip all this. So what I'm showing here is just the general guide word. Like, for example, when we say no, not, none, these are one of the guide words, higher or lower. So for example, when we say, okay, I want to check on the flow rate of this pipe as your HAZOP analysis. So the first thing, if let's say we use no flow rate, then you use the first guide word as no. No means no flow rate. And the next questions we are going to ask is like, what could go wrong with this? What could cause no flow rate? And what's the consequences of having no flow rate in this pipe? Okay, and then we want to come up with a preventive measures to prevent for the no flow rate. And also we want to have a detections method to detect what is the consequence, like how do we know when there is no flow rate? Okay. So then we go to the second one. If higher flow rate, then if you're setting it at 10 liter per minute, and when you check, it's running at 20 or 30. So the first thing you're going to ask, what could cause this higher flow rate? And then the next question is, what's the consequences of this higher flow rate, etc. And so with the lower flow rate, and also these are other guide words as well as normally used for like mixer. If let's say you have two different streams, you have chemical A coming in this piping, chemical B coming with this piping. So what other things that could happen at the same time? Okay, so part of is where some of the like reactions, not all your reactant has been reacted, so only part of it has been reacted. Then you want to ask what causes that part of reaction. Okay, reverse normally work in flow or chemical reaction. So when you have a reverse flow rate, what does that mean? What causes the reverse flow rate and what's the consequences of the reverse flow rate or chemical reaction? Then we have other than. Other than is like when you have chemical A supposed to come in, but what happened if chemical C came in? So that's where you want to look at like what really went wrong. Did I have a maintenance where the contractor connect a wrong piping? Because those things happen. Or if let's say you have a timer, when we have sooner than later than, it's always talk about process step or an actions, or it always involve a timing. Okay. And where else? Like things like what are the locations of operating procedures, etc. So the primary keywords, the normal things that we both study in a HAZOP analysis is always on flow rate, temperature, pressure, level. And if let's say we are talking about separation processes, then we want to look at how well the separation is, the compositions, if let's say you have a reactor or a mixer. And then we want to look at the reaction rate or the mixing rate, and etc. Okay, so the first few is the main one. So you can see flow, then we have only a few guide words that you can use. In the complete HAZOP analysis, we will test on every single guide words. We will actually brainstorm on every single guide word what could go wrong in terms of flow rate. And in today's practice and also in your exam, I will not need you to do every single one, okay? It's just a few, take 2 or 3 will do. So in exam, this is normally a 15 marks questions. So if you read the questions carefully, normally I'll ask you to choose 2 process parameter, 3 guide word each, and give 1 or 2 potential cause and potential consequences. And the one that I focus a lot on is always the last part, the what we call the actions part, like what actions do you want to take to prevent this, the prevention, as well as the detection. Okay, so these are more of these words that you can look at it. Okay, and so in HAZOP, because it's a brainstorming exercise, so it always have assumption. But when we want to do assumptions, right, we have to assume something that is logic, that is practical. If the assumptions are not valid, right, then your HAZOP has no meaning. Okay, and also in HAZOP analysis, even though sometimes we may say the potential causes are natural disaster like earthquake, like volcano eruptions or like tsunami, etc. But we can't take any actions to prevent those because we can't prevent natural disaster. Like in Malaysia now, nowadays we have a lot of things. The natural disasters, we call that as flood, flash floods, storm with all these trees falling along the roadsides and all that. Those are considered natural disaster or landslides. We can't prevent them, but we have to be able to detect them, and the actions must be taken. Like when this happen, what actions do you take, yeah, to prevent further catastrophic from happening? Okay, so this is the general form for HAZOP analysis. So you can see the item. Item here is where normally it's just a number. Study note is where you want to identify from where to where you want to study. Like, because the process itself is so huge, you may have like 10 different unit operation. So if let's say we in HAZOP study, we have to be very focused. Sometimes we only study one process, meaning one unit operations like a reactor. Sometimes we only focus on one pump itself, or even one valve, or even one like piping flow. If let's say that is a hazardous line, we will do that. And in fact, you have to write down very clearly into study note from where to where is your study. And then your process parameter is what I mentioned just now, like what are the parameters over here that you can see: level, temperature, pressure, and etc. Okay. Then your deviation means your guideword, the no flow rate, higher flow rate, lower flow rates, reverse flow rate, and all that. That's where then you put in the possible causes for no flow rate, or higher flow rate, or lower flow rate. So every guidewords you need to have at least one to two possible causes, and what are the consequences when you have no flow rate or when you have higher flow rate. So that's where you want to see, is this bad, or is this something that I can ignore? Is the risk worth to take it if I'm not taking any action? Okay, so what we will focus a lot on is basically on this part, the actions required. You get a lot of marks on your actions here. Okay, so there are two ways. One is what I call that detection. Okay, another one is prevention. So when you have detections, normally you will get only like 1 mark. But when you have prevention, okay, we'll give at least 2 marks. Okay, and when your HAZOP analysis only have detections but no prevention measure, okay, you will not get a full marks for your HAZOP analysis in your exam or in your assignment. So far, any questions? We're going to go into detail as exercise so that all of us work together to look at HAZOP. So I'm going to stop here for this one. Okay, so allow me to share screen on the other one. Okay, so what you're looking at is okay, not this one. So what you're looking at is the HAZOP analysis on this heat exchanger. Okay, I have given another example in the presentations on the reactor. But what we are going to do today is on this heat exchanger. So hold on a minute. Let me just share this link again in the chat box in case those who came in late doesn't have that. Or you can actually get it in your My Times. I just add in the tutorial discussions in your My Times mode here. So you can just click on the link and you will come to this as well. Okay, so let me just share the link again. Okay, and so you all can click and come in here. Okay, so let's take a look at this HAZOP example. So we have this study note that we have this volatile solvent coming into this heat exchanger at a high temperature, at a low temperature, and then you want to heat up the volatile solvent. And so you have steam coming in, and then condensates going out on your heating stream. So we want to identify the study notes of the process. So today, definitely we want to study on the volatile solvent. So the HAZOP analysis studies on the intentions of hot solvent from heat exchangers recommend possible modifications to improve the safety of the process. So the process parameter here, of course, our study notes will be only on these volatile solvents into these heat exchangers and coming out. So we want to be very focused on that line. So when we talk about flow rate, we only talk about volatile flow rate. So if I were to put this like what we have just now, let me insert a column to the left. So study note. Okay, the study note here will be your volatile solvent stream. Okay, meaning we only focus on that. That includes one of the valves here and also include the temperature control system. Okay, so here's what we are going to have. So the first process parameters, of course, when we look at this, definitely is the flow rate. Yeah, so when we talk about flow rate here, so of course we want to say no flow rate. Okay, what potential causes no flow rate? Could be valve V1 close. Okay, so in that case, what are the possible consequences is that there's no supply, no output from the solvent stream. Okay, so and if let's say we want to go more detail in that, the first one is when you have no output, what could go wrong? If you know the next process, then you can put in what is the consequences or what is the impact towards the next process. But at this moment, we have no idea what is our next process here. So what we can do is just, okay, we are going to stop that. There's no output. So how are we going to detect this or how are we going to prevent this from happening? Okay, so and we always put a P or for prevention, D for detections. D, you may want to put a flow meter in line with alarm system. So you want to put in a flow meter that with an alarm system to tell you when there's no output, there is no flow, it will ring. Okay, so with that, in fact, this itself, you can do it for multiple system. So very often we'll put like 1 here to tell us, okay, this is number 1. And that flow rate is also 1 here because later on you have 2 on this one. And so this will be your 1.1. You see, over here, I put 1.1.1 means if let's say I want to put more things in here, like if I want to have, oops, 1.1.2 means it's still at the 1.1 section, okay? So over here, if I want to have a preventions, any way to prevent it? I would say perhaps no for this time being, unless you want to automate the system on the WAF. So you may want to change V1 to a automated WAF. Okay, so those are the possible things that you can do. Allow me to go and change this to top. Okay, so now we have 1.1 on no. And so do we have other potential things that can go wrong for no flow rate. So if no, then we go to low flow rate. Okay. So so this is 1.2. Possible valves also that someone close it, operator close accidentally, reduce the valve or reduce the setting of the valve. Okay. So possible consequences. This is going to be high, be on the higher consequences because you have a steam coming in, and your flow rate is lower, means you will have a higher temperature output of the volatile solvent. Do you see that? When we have no input, you don't have any output. But when you have a little bit of input, the consequences is actually worse because then meaning your volatile come out is hotter. And because it's volatile, so it might contribute to a runaway system. When we say a runaway system, where then it is like if it's going to a reactor or a mixer, the reactions you can imagine with a higher temperature, because if let's say it's supposed to come in at 25, go out at 50, but because we lower down the flow rate, it goes to the next process at a higher temperature. And instead of 50, it may go in at 60 or 70. Means that if let's say the next process is a reactions process, your reactions may be more vigorous. And in fact, that may cause to a runaway reaction system. Okay, so then this is something that we may want to avoid. So let me put it at red, because this is something that we really need to take actions to. You can have no flow rate, but you can't have a lower flow rate. Do you see the differences here? Okay, so over here, what do you want to, okay, the detections will always be the first one, the flow meter in line with alarm system. But here we have a prevention here. Okay, so this is 1.2. Okay, alarm. Detections, flow meter with alarm. But we also can have another prevention, is where you can see that the control valve is that temperature control system that reduce the flow rate of steam. As you can see in this system, is already in that. That is actually a prevention from higher temperature output. Can you see that? Yeah, meaning it helped us to control. If let's take a look back at this one. When the stream come in here, is there any way I can draw? Over here. So when we have the stream coming in here at a lower temperature, so the temperature here is going out to be increased. So over here, it feed back to this control system to say reduce the flow rate. So when you have reduced flow rate, what happens is that it actually helps to maintain this temperature. It helps us to maintain the temperature of the output. Okay, so this is what we call a prevention from getting a higher temperatures output. Okay, but does it prevent someone to reduce the setting or set a wrong setting of the valve? No, it prevents a higher temperature coming up. So even on preventions itself, okay, so let me just remove all these. Even from the prevention itself, as you can see, there are two types. This is to prevent a high temperature output. But this does not prevent your equipments, the operator, it does not prevent the possible cause. It prevents the possible consequences. So over here, the actions can be for consequences. The actions can be for causes. So as engineers, we decide what is more important for us. Over here, you want to reduce the chances of having high temperature. Okay, so you put in the control system, which is already in the system here. Okay, so for us, this one actions already taken, we don't have to worry about it. But if let's say there is no such control system, then the next thing, immediate things that we need to do is to put in this control system in this heating the heat exchanger system. Okay, any questions so far? So this is how we do HAZOP. So what I'm showing here is just a very simple, what we call the uh, example, so that we can have an idea on what is going on in here, how do we want to prevent things from happening, and how do we set a HAZOP table. So far, any questions? So in your exam, okay, as I said, this is a 15 marks questions. If you have these 5 columns, because sometimes people can put your study notes up. Okay, sometimes people put the study notes in the table. It doesn't matter. But in your HAZOP table, this 5 column is a compulsory, it's a must. First is your process parameter. Okay, because it tells us which process are you looking at. And then it tells us which deviations or what is your guide words that you are analyzing. Okay, and then the possible causes, the possible consequences, and actions required. So when you have this, okay, you means you won't get marks for having all 5, but any column missing, total marks -2. So if let's say you only have 4 columns, for example, okay, whatever you do, you get marks here, but your total marks here, if you get a 15 marks, it won't be 15 marks, because when you have missing columns, you already have missing marks. If let's say you get a 10 marks, for example, out of 15, and from this 10 marks, you will get another 2 marks minus for insufficient column for the formatting. Okay, so there will be no additional marks given for correct columns, but in the exams, marks will be minus if, let's say, you forgot about which columns to have. But it's very easy to remember, because when we talk about HAZOPs, we talk about process parameter. Okay, so after your process, the next thing is you want to look at after the parameter chosen, the next thing is like the guide words, because it guides you to look at what could go wrong and what will be the consequences. So that itself already give you guide words, parameter, guide words, causes, and consequences. And as I mentioned, the most important thing is that the actions that you need to prevent or to detect the wrong over here, the causes or the consequences. Okay, any questions so far? If no, then what we are going to do here is that we have an example here. Okay, so you can see there is this. Let me just remove this. Okay, so you can see this is actually the examples that in one of the presentation, the recording. So we have the reactors, we have the monomer coming in, and the cooling system, water going in, going out. So there is a few systems here. You have your monomer coming in here. Okay. Your monomer coming in here. Okay. And then you have your cooling water from this system and go out from here. Hey, how come I have this weird things that will move away? Okay. So the cooling system itself is a one HAZOP analysis. The monomer here is another HAZOP analysis. As you can see, there is also another stirrer. Okay, okay. The stirring itself will change the reaction. So the stirring itself will also be another things that we will study. So now what I will want you all to do is that allow me to just undo all this. Okay, well, I'm going to split you all into two groups. Let me see how many people we have today. Okay, so six of you, three in a group. So group one, you will focus on the cooling water. Okay, so group one is on cooling water. Group two, you will focus on the reactor temperature. So one is only on the cooling water in and out. The second teams, you will focus on the reactor temperature to run a simple HAZOP. So the process parameter here, you all can choose what you want to do lah. Okay, this one hang already. Need to choose the computer today is a bit lacking, so forgive me. Okay, so you can actually copy this picture here. So that you know which one what you are looking at. Okay. So group one and group two, you don't have to worry because I'm going to split you into groups now, and then you can start working on this hazard identification. Okay, just allow me to stop sharing so that I can put you into group. Any questions so far? Is that clear on how we do hazard analysis before I split you into groups? Yeah, so remember group one, you will be focusing on the cooling system, the cooling water. Second group will be on temperature of the reactor. They are linked, by the way. So that's why I'm putting you on this one. Okay, to breakout room. Okay, the breakout room has been set. So you can go into your room now. Hey, you know what to do, right? Just to focus on the cooling system. So you choose your process parameter, you choose the deviations, and then you start working on it. Yeah. So I would say two deviations, and yes, I would say you choose like one. I think there's only one or two parameters here. One of your parameters can be flow rate, the other one is a temperature. So then for that you choose like one or two deviations, I would say, for each parameter, and then two causes for each deviation. Then you work from there. Okay, I'll come back to you all. Let me go to the other room first. Any questions before I leave?
No, miss.
Okay.
Cooling coil and a thermocouple. Exothermic reactor system with a cooling coil and thermocouple.
Just interrupt a bit. You know what to do, right? Okay, so yours is on the reactor where, if let's say you look at it, there's this cooling coil to cool down the temperature because you want to talk about your temperature system. Yeah. Your reactor temperature. So what you can focus on, you can be focusing on your temperature going up and down, and that itself is your process parameter already. So then you focus on too high, what will happen, too low, what will happen, uh, and then you work from there. No need to be too long. So one parameter, two deviations, and two causes per deviation. It's just an exercise for you to see how we construct the HAZOP analysis. Yeah, I'll come
Please,
back.
can you send me the Excel file in the chat here again, please?
Come again.
Can you please send the Excel file link again?
Okay, sure. I'll do that now.
Miss, we cannot type in the Excel.
Cannot type. I thought
Yeah,
can.
it's protected, it says.
Oh, I have already allowed everyone to do the typing. Hold on
Let me
now.
refresh.
Yeah, maybe need to refresh.
It's still locked for me.
It's still locked.
Yeah. Yeah, your group 1 and group 2 both also cannot type it.
Okay. In that case, how do
Yeah,
I?
protected.
Let me see how to. Okay, let me close the protection. Check and see. Can you type again?
Yeah, we can. Yeah, it's working now.
Yeah, working now.
Okay.
Okay.
Let me just go to the other room. So y'all just take about 20 minutes to work on this, then we can proceed with the discussion.
Okay.
Hi, sorry, just now the spreadsheet was protected. I already unprotect it, and so I think you all can type now. You all test and see. Can? Okay, cannot?
Now can, miss. Now
Okay,
it's okay.
okay.
Yeah.
I'll get back to you all. Take about 20 minutes to get this done. Just a quick one will do. Okay, so welcome back, and let me share the screen and you can look at what we have here. Okay, so let's take a look at what we have with group 1. Anyone to present? So you're working on the cooling system for reactor A, so you're looking at 2 different process parameters. So over to you, group 1 who wants to present. Anyone? Come
I'll
on.
present it, Miss.
Okay, sure.
So the first process parameter that we looked at was temperature, and the temperature could be high, so that's one of the guide words. And this could probably be due to a faulty thermocouple. And the consequences is when you have a faulty thermocouple, you have bad temperature detection, and leads to bad valve activation for flow rates. And because of that, it could lead to explosion because of heightened pressure. And the action required for detection is to install temperature sensors to detect an unusual rise in temperature, and the prevention is for regular service of the thermocouple and valves so that the automated system works properly. Then the other one is flow rate. The deviation for flow rate is if it's less, which would lead to less cooling. So this could be due to a partial blockage in the line or a pump malfunction. And the consequences is a gradual temperature rise and reduced reaction efficiency. And the action required for this to be detected is to install flow meters to detect and alert operators of low flow rates so that they can rectify it. And the prevention for that is the prevention action is regular inspection and cleaning and monitoring of the pump performance.
Okay, thank you. Yes, that is about it. So you can see it's actually very simple to do a HAZOP analysis for a simple one. So what we are doing here is just the I would say we touch on the very surface on like how a HAZOP should look like. But if you go into detail, right, at the end of the day, if you really work on the whole system, right, this reactor itself may give you 5 or 6 pages worth of data and information, because if you're looking at like now you only look at high temperature of your cooling water, so meaning cooling water is supposed to come in at around maybe 10 degrees Celsius, and instead it come in at room temperature. That itself is already an issue. So high temperature or low temperature, so it's supposed to come in at 10 degrees Celsius, but it comes out even lower than that. So if let's say we look at each one of the deviations, you'll notice that your HAZOP analysis becomes huge. Anyway, but what we are practicing here today is just so that you know, okay, this is how I can do HAZOP analysis. So in fact, knowing how to do a HAZOP analysis is a very powerful tool. And if let's say in the future, if you go for interview and all that, like if they ask you, do you have any concepts on safety and all that, you can just tell them, oh, we actually practice a bit of HAZOP analysis in the class, but on the very surface on what other things can be done and what is needed to be done, etc. But tell them it's on the very surface area level. Okay, thank you very much. One thing I want to bring up the attention is that in HAZOP analysis, very often the first thing we do is for detection is always to install alarm. In HAZOP, yes, you can put in all the alarm system in there, but in practical, then later on, we actually have to choose what are the critical alarm to install, because we won't be installing every single alarm in here. Because you look at this cooling water itself, you already have one temperature alarm and then one flow meter detections and all that. So all these detections means to identify or to notify your operator means it comes with alarm. So we do not want to, we only want a few alarm systems so that when the alarm rang, the operator take actions. When you have too many of them, means what you're going to hear first, you're going to hear a symphony in your process line because it will ring all the time and with all the different pitches and all that. Second is that when you have too much of alarm, people start to immune to the alarm and people won't take actions on it. So that's why I say when we do HAZOP, we put in all the alarm that is needed. But when in real actions, then we have to identify which one is the critical alarm to put in. We only install those. Yeah, so when it rang, the operator must take action. Or sometimes we will even convert some of this alarm into a higher level of control system. So that, like for example, here we have the flow rates and all that. So instead of just putting a flow rate, in fact, we may have put in a flow control system to increase the flow rates. And if let's say it can't increase any further, only then the alarm will ring, etc. Okay, so any questions for this one? Very well done. Very good. So let's go to, if no, then we go to group 2. Okay, over to you. Group 2 talks about the temperature system or the reactor temperature itself. So anyone from group 2? We have Bernard Junhan and Muhammad Ehsan. Anyone? Come on, please.
Okay, I'll present.
Okay, thank you.
So the process parameter will be the reaction temperature, and the two deviation is either the too high or too low of reaction temperature. So let's go for too high first. One of the causes will be either the low cooling water flow rate, so the temperature will be high, or the cooling water temperature is too high, so there won't be much heat transfer between the reactor and the cooling water, and this will lead to possible runaway reactions due to high temperature. The detection will be adding the flow meter in the cooling water supply, and put alarm as a warning, increase the water flow rate changes to too low. And the prevention will be leak detection system in the cooling water supply to identify and locate any leaks in the supply before it impacts the flow rate significantly. And the second cause will be malfunction in thermocouple. So if the reaction temperature is too high, it will cause a temperature spike, which will lead to the pressure spike and then eventually brings a vessel rupture due to the pressure. And the detection will be installation of multiple thermocouples and compare readings between them to detect any differences. And the prevention will be using dual element thermocouples, which is also multiple thermocouples to provide a backup in case any of them fails. As for too low of reaction temperature, it's either the high cooling water flow rate or the cooling water is too low, so the heat transfer is too much. And this will lead to the decrease in reaction pressure, and the pressure might be too low for the reaction to be initiated, to be running. And the detection and prevention will be the same as above. And there's the same for thermocouple malfunction also. For the thermocouple malfunction, too low of the temperature might create vacuum because the pressure is lower than the atmospheric pressure, and it will also cause vessel rupture. Thank you.
Thank you very much. This is a very clear what's called the HAZOP analysis table. Yeah, so if let's say you can do this in your exam, I believe you can easily score the marks in there. Also in your assignment. So any questions so far on HAZOP analysis? Because we have two parts of it today. HAZOP is only the first part. And then we have today's topic is mainly on hazard identifications. I think if you look at the tutorial questions, we have another 4 questions in there. So let's see. So now we have 7 of you. What I will do is I will split you all into um hmm, 3 groups. Okay. The first there will be group of 3 and group of 2 and group of 2. Okay, so the group of 3 you will have to do 2 questions because that's where I think this will be the easy questions here. So I will give you question 3 and questions 5. Okay, for the 3 persons group, and then the other 2 persons group will be questions 2 and question 4 each. So what I will do is, like, if you look into the group later, it will show names, and later also I'll put in the names here so that you know which one is done by you all. So you all discuss, and also another 20 minutes. We'll come back in 20 minutes time to really look at your answer. Just give me a moment to again open up the group, the breakout room, yeah? Okay, one is missing. Who is missing? Just now, I think one of you dropped out. Let's see. Bernard's here. Rashini A. Who's missing? Okay. Anyway, when the person's coming, I'll put him in that group then. Okay, this will be question 2. So once I open this room, you all go to your room, and also the one of the group you'll have 2 questions, but those questions are very simple, so I believe you all can do it easily. Yeah, so I'm just going to open up this group, and if let's say your classmate come back, I'll put them into the groups that has 2 questions. So you see your group called Q2, Q3, Q5, and Q4. Here you go.
Hello.
Okay, you all can do, right?
Miss, I do you have the access to the slide? I cannot access to the slide. Like I don't have the link.
I thought I copied the link again. Hold on, yeah. If not,
Okay.
you can actually go to my times to look at it. I put it in the chat box again. Hold on,
Okay.
you'll be able to see the chat box.
I will be able to look at the chat box. Yeah.
Okay, just click
Okay.
on it, and then you can go into.
Okay. Thank
Yeah.
you, Miss.
Okay.
You put
All good, right? You can access to the file.
Hi, Miss. Where Can I know where are the questions?
Okay, it's in the file, in the link. Can you see the link? I put it in the chat box. Can you look at the chat box? There's a link there.
Don't have more.
Don't have ah? Okay, let me copy again and see if you can get this.
Oh yeah, I get it ready. Okay, thank you, Miss.
Okay.
Question 2.
Hey, did you all get the link to get into the files? No. Okay, cool. So y'all will be working on 2 questions, yeah. Question 3, question 1, but they are very simple question, very straightforward questions. So that's why even 2 or 3 persons will be able to do it very quickly. Okay, I'll get you all back in the room in another, I think another 14 minutes, yeah. Give you 15 minutes. Okay, sorry, I didn't realize I was muted. Okay, so let's look at these questions too. Bernard or Hasini, can you present? One of you?
Yes, Miss.
Yes.
I will be presenting the main hazards first, then Hashini will be presenting the effective safeguards later.
Okay, sure. Thank you.
Okay, so for my part, there are basically 3 hazards for here. For the if we purchase too many robots to facilitate in our production line. So the first one may be the programming and control failures. The errors in the robot's programming or control system, it will cause unexpected movements or malfunctions, leading to safety incidents such as injuries or even fire hazard or something. Because this one the programming things will cause the next 2 hazards also. The second hazards will be the electric hazards, then the high voltage system of the robots, and the exposed wiring outside, it will cause electric shock or burns And the faulty wiring, it will lead to short circuits and also posing fire hazards if the short circuits remains without any fire rescue team here. So this is for the electric hazards. Then the third one will be the mechanical hazards, like robots. Robots are made by steel or something, so they will generate high forces or torque, which can cause injuries if a worker is caught in the robot's path, because these robots' path are already programmed. If you didn't notice that the robots is moving, it will probably just injure you in any other way. So the mechanical failure also can cause the objects to be ejected from the robot if the maintenance team doesn't did it well, like the screwing or something. So it will potentially just strike the workers in also any other ways. Yeah, this is for my part. Thank you.
Okay, thank you. So let's go to Hasini part.
Okay, so for the effective safeguards, take into account of the control measures. For instance, can install the emergency stop devices. These devices ensures that robots are equipped with easily accessible emergency stop buttons, or pull the cords that immediately stops all the operations. Next, by installing speed monitoring system, this system implements speed and proximity monitoring systems that reduce the robot's speed or stop it when a worker approaches a predefined safe zone. Next is administrative controls. Training and education should be provided to all the employees on the safe operation, maintenance, and programming of robots. This includes recognizing hazards and understanding emergency procedures. Next is taking into account of the standard operating procedures, the SOPs, developing and enforcing the SOPs for working with and around robots, and this ensures that the procedures are regularly reviewed and updated. Next is regular maintenance and inspections. For instance, routine checks, conducting regular inspections and maintenance of robotic systems to identify and rectify potential hazards. That's all for my part.
Okay, thank you very much. Wow, this is a very good analysis. But I think right now one of the things on robots, because we all know that we are going to automations, a lot of manufacturing processes, productions are into robots and also automation. Besides what you have listed here, I think the other concern right now is it is subjected to virus or intentionally or unintentional attack, cyber attack. So cybersecurity becomes a very important matters over here. Yeah, so because we all know all these are linked to computer system, and computer system, all of us know, is vulnerable to virus. Yeah, so antivirus system is a need, as well as a good programming system is a need. So this is some things that our manufacturing is moving towards. So as an engineers, we also always have to be well equipped with computer skills. Yeah. Any questions on this? If not, then we will go to question 3. Over to you, either Bernate or Junhan.
Okay, I'll present. So the operator was told to control the temperature at 60 degrees Celsius, and then he set the temperature controller at 60 degrees. So the set point temperature would be 120 degrees Celsius.
Mm-hmm.
And then any modification to prevent similar accident for the overpressure would be, first one is clear labeling on the temperature controller, so that the controller is marked with actual temperature, the numbers, any like the numbers and not percentages, so that it will be clearer. And then second will be training, to ensure the operators are trained on setting and determine the control parameters accurately, so that they know what they are setting at. And then third one will be interlock system. Can install the system to automatically stop or alert operators at any unsafe temperature, maybe above a certain temperature. And lastly, maybe lower the set point temperature lower than the 60 degrees Celsius to prevent any accidents.
Okay, thank you so much. Yes, you got it correctly. And so what happened over here is that this is actually a very common error or mistake in the manufacturing, by the way. Allow me to just make this smaller so that I can actually draw next to it. Okay, so you can see this operator was told to control the temperature of a reactor at 60 and it set points controller at 60. So what happened is that if let's say there is a indications here, let me just draw. Okay. So 0 to 100. Okay, so what happened is that the scale is actually in terms of percentage, but if let's say some of the scale or the knobs is just like this, and so a triangle. Sometimes in the old manufacturing system, this is what we have, a very old-fashioned knob with an indicator. But when the indicator doesn't shows what are they, it is our job to make sure operator don't do it wrongly. So what happened in this case that it shows 0 to 100, but it didn't tell what is that indicate. So when the operator is asked to set it at 60 degrees Celsius, so immediately the operators do this one. So this is 50, for example, so 60. So the operator set it to here. Instead. But in truth, what we are actually having is that this is not degrees Celsius, but this is in terms of percentage. And it is actually from 0 to 200 degrees Celsius. So when we have 0 to 200 degrees Celsius, what does that mean? The 60% here means this is actually 120 degrees Celsius, like what Jun Han has mentioned. So what they need to do is actually add the 30 here to set it here correctly. So as engineer, right, to prevent this from happening in the future, because sometimes when we go to the manufacturing, what happened is that the machine is fixed. We can't change the machine. We can't change the knob and all that because it comes, the machine may be 20, 30 years old. So what we can do, I like the interlock. You install the system to stop and alert at unsafe temperature. But for us as an engineer, sometimes we can just do a very simple thing. Instead of asking the operator to set it at 60, what we'll do is get a sticker and then stick it like this. Cut it to a triangle and stick it at the controller like this. So you don't have to tell the operator 60 degree or whatever. Just ask them, this is the indicator, put it there. Or you can tell them 60 degrees Celsius, follow the indicator and you put an indicator there. Okay, so that's a very straightforward, simple solutions or simple way to identify, to tell the operators, okay, this is where the set point should be. Okay, any questions so far? So sometimes these solutions can be very simple. As engineers, we have to be creative. And these are real life examples here. It happens in manufacturing before. Okay, question 4. Over to Esa or Pravindra. Okay, I think one's missing. So
He's missing, so I will present it.
okay.
Okay. So, do I read the question or just the answer?
Okay, let me just read the question for you then. The liquid level in storage tank are frequently determined by measuring the pressures at the bottom of the tank. In one such tank, the material stored in the tank was changed and an overflow resulted. Why? Yeah.
When changing the material stored in a tank, the density and the viscosity of the new material can significantly affect the pressure existed at the bottom of the tank. If the new material is denser or more viscous than the previous one, it will exert a greater pressure at the bottom of the tank for the same liquid level. This can lead to the liquid level measurement potentially cause a tank to overflow if the liquid level is incorrectly perceived to be lower than it actually is.
Yep. So this is a very old way of measuring liquid level. And it is still used as mentioned, because one thing in Malaysia, or if let's say you're working in any other developing countries in the future as process engineer, you realize that they use a lot of old technology. One of them is the way of they measure level. So this old way of measuring is by checking the pressure of the tank, and they use density to backward calculate that what is the total volume, and with that then they estimate what's the liquid level. So when you have a different chemical, okay, the density of the chemical changes. So when the density of chemical changes, if you have a denser chemicals, it gives higher pressure at the bottom. So what happened is that denser materials, you actually have a lower volume. Yeah, because of for the same volume, it actually shows a lower volume in the tank. But if you have a lighter, like for example, you change from water to oil, the next thing is you're going to have an overflow, because if let's say you didn't change the setting in the level of the measurement, you pour in this what we call the oil, because it's lesser, it's dense, is lighter. So the pressure will say, oh, this is so light, and so this is the level. And even if it's at maximum level already, it will still think that it is actually lower than it. And so what happened is then you get an overflow. So one actions we can take as an engineer is that whenever we do changes, that's what we call in chapter 1, we call it the management of change. Change management is very important to prevent all these things from happening. Meaning, if you want to change anything, there is a process to change it. And so when you change it, then you have to test, and you have to actually change all the SOP so that people will not make mistake. Be it the earlier mistake like here or this one. Okay, any questions so far? If no, then the last questions, this is a very simple questions. Let me remove their name. I'm going to just show you what to do with, because safety questions sometimes can be as simple as this. A good acronym in chemical plant design is KISS. Keep it simple, stupid. Sorry for the word S, the last S. But this is what we use. Just want to make things simple, because the simpler it is, the less hazard it presents. So complicated design are almost always more hazardous than the simple one. So in this figure, you can see that to maintain a sample, the level, okay, is maintained at the maximum height. They use a pump, they use a level control system, and then tell the pump, okay, now it goes beyond it. So let's pump up some chemical from that. And so this is actually quite a complicated system. Why? Because you have to maintain the pump here. You have to maintain the pump. You have to maintain the control system. Anything that goes wrong, your system will have overflow. So a simpler way to change this is actually what you need to do is you just have to open up. If let's say this is the maximum, all you need to do is to drill a hole there, put in the piping, and connect it to another containment plant. And you don't need a pump, you don't need level control system, you don't need valves, or you don't need any control system to operate the pump. You release all those needed unnecessary or additional maintenance over here. And also this system, as long as it goes above it, it goes to containment the containment tank. So you won't have an overflow system. Okay? Any questions? So is that very simple? So in the exam, if let's say you're given questions like this, one of the tips for safety is to draw. If you notice just now, the earlier questions also I used to draw it. And also these questions, you just have to draw. You can even draw on the if let's say like in your test, for example, because your test questions is I will ask you to answer in your test questions, or maybe you give exam script. If let's say you're answering in the test questions, right? All you need to do is draw on the diagram itself, just overlapping drawing on it and say, okay, this is the solutions, like what I did here. Yeah, so what I did was just this 2-line and new piping system, and perhaps I would just add in to containment, or we call it secondary. Okay, let me just write down the full word. And then we treat it, and then we release the some water into the river after treatment. So this is what we can do. Very simple. You don't have to even worry about pump maintenance, controller maintenance, etc. Any questions? If no, then that's it. It's already 12. Next week is your test. So give me a bit of time here. Next week is your test 1 on Wednesday. Yeah, we are using our tutorial slots for the test. There's no change in the venue because there's only 7 of you. So we are going to use the X space. I'm going to just split like 2 tables with 2 people, then the rest 1 table, 1 person. And that the topics that we cover is introductions to safety, which include those HAZOP analysis, the process system management, not the HAZOP analysis, sorry, the OSHA indications, OSHA rate, what is that called? There's a few rates in there's few calculations in chapter 1. Suddenly my mind just go blank. And then we talk about chapter 2, toxicology, how toxicants enter the body and how toxicant eliminates from the body. And we talk about simple calculations on what is TLV, TWA, STEL, and sealing. And then we go into industrial hygiene, talking about control of the toxicants in the workspace. Then in chapter 4, we talk about relief system. Yeah, the relief systems talk about all these reliefs. Well, where do you put them? How do you install them on that theory part? Okay, so 4 topics will be covered in test 1. Test 1 is 15%. So I see you next week. What you need to bring is your calculators only. The booklets will be provided. Yeah, the safety data booklets will be provided. Okay, any questions so far? And also, I'm going to release what is needed in your assignment 2 very soon, but you already did part of it because as this week also, I'm going to ask you to take another iChair classes, because here you take 1, this is already 3%. So hazard identifications, iChair site, they have more details on how to do hazards analysis. So I'm going to upload here today. So you have about 2 weeks by week 8 to complete hazard identification. And then week 8 also, there will be another chapters on fire and explosions. So I will also upload the chapters to study in iChair. So that will cover 2 or 3 topics already. And because week 8 is a self-learning week, means there's no classes in week 8. And week 7, the Wednesday, we have tests. So Thursday, there's no class on the lecture, but you are going to have your industrial visit to KLK Oleo. So please go for that. So far, I think only 1 or 2 students in this class has signed up. So if you have not, please, I will upload again in the WhatsApp on the link. Please sign off, and then so that the lecturers can do the necessary arrangement for the visits on next Thursday. Okay, so I think for next Thursday, the PIC for the visit is Dr. Shinjikai, the new lecturer, and Dr. Rashmi also will be going together as well. So together with all of you lah. So I think that's about it from my side. Any questions? If not, then I'll see you next Wednesday for the test. All the best. Thank you.